Calculating currents in the bipolar junction transistor necessitates that we take a look at which components form these currents. So let's take another look at the BJT in active region. So as we said, what's happening here is that we are injecting a lot of electrons from the emitter to the base, a lot more than there are holes being injected from the base into the emitter. The reason is, of course, the differential doping. Some of these electrons are going to make it into the base metal contact and will form a base current. Many of them, if we design the BJT properly, are going to reach the depletion region. The depletion region has a favorable electric field that will sweep these electrons into the collector. We can also see that the electric field is favorable because the slope here is conducive to the flow of current. So we actually see current flowing through a depletion region. How come we didn't see that happening in the PN junction? Because in a reverse biased PN junction, you would never see a lot of electrons on the P side. Remember that the reverse saturation current in a PN junction does consist of electrons moving from the P side to the N side and holes moving from the N side to the P side. But there are only so many of these in a PN junction. Here we have a third terminal, which is the emitter, which is pumping a lot of electrons into the base, which is P-type. Thus, we can see a lot of electrons moving across the reverse biased base collector junction. So let's take a look at how a bipolar junction transistor is actually fabricated. And it's really important that the base is very narrow, and it's really important that the emitter is more heavily doped than the base. And this is how a BJT with favorable properties can be fabricated. Our first instinct would perhaps be to fabricate the BJT this way, NPN. And this is indeed a BJT, but it is a BJT with bad properties. And the reason it has bad properties is that the area between, the width of the base is actually large. If we examine what's happening here, the width of the base is really narrow, and also the collector surrounds the base. So the common area between the base and the collector is really, really large because the base is sandwiched within the collector. Why we do this? Because what we want to do is when we pump electrons from the emitter into the base, these electrons are going to do one of two things. Some of them are going to reach the base contact and thus form a base current, and some of them are going to reach the collector depletion region and be swept into the collector, forming the collector current. Using this structure, we make sure that the majority of electrons actually make it to the collector, and only a very small proportion makes it to the base contact, forming base current. So let's go back to our conceptual view of the BJT, and we know that this is not how it's actually fabricated, but it's helpful just to think of it this way sometimes. What's happening here is that we are showing the flow of charge carriers, and we mark them using currents I1 through I6, but they're actually charge carriers. We want to look at each one of these current components and think about what it represents. So I1 is the injection of electrons from the emitter to the base. So these are the electrons that go from the emitter to the base. Why do they go from the emitter to the base? Because we have a forward bias PN junction. The mechanism which moves them from the emitter to the base is diffusion. And this is a normal process that happens in a forward biased PN junction. It is just the injection of excess minority carriers into the other side. This flow is really healthy because we have a high concentration of electrons in the emitter due to the heavy doping, and therefore I1 is an extremely heavy flow of electrons from the emitter to the base. And there's nothing weird happening here. It's just what would happen in a PN junction. Also, what would happen in a PN junction is I4. And I4 is the pumping of holes from the base to the emitter. So when we looked at PN junctions, the diode current was formed not only of electrons moving from the N side to the P side, but of holes being diffused from the P side to the N side, which is I4. So again, it's important to notice that the arrows here represent direction of flow of charges, not directions of currents. And so I1 is the flow of electrons, and the corresponding current is in the opposite direction. I4 is the flow of holes, and the corresponding current is in the same direction. So I4 is a very small current. I4 is a very small charge flux. Why? Because the base is much less heavily doped than the emitter. And so we can say that I4 is much smaller than I1. And this is because of the differential doping of the base and the emitter. So what is I2? Let's now talk about I2. I2 is the proportion of I1, the injected emitter current, which goes to forming the base current. So if we had a p-n junction and we injected electrons from the n side to the p side, these electrons would eventually turn into holes, and they will continue to carry the same amount of current into the p side and out into the metal contact, so that we have a complete circuit. This is what we saw when we looked at the p-n junction. I2 is the amount of electrons that manage to recombine within the base. And when they recombine within the base, they absorb holes, and these holes are replaced by a diffusion of holes from the metal contact, which forms I3. So I3 is the hole current that is absorbed from the metal contact of the p-n junction to replace those electrons that recombine within the base, which is the normal process through which p-n junction or diode current exits through the metal contact. In this case, however, normally we would assume that I1 would be I2. So in a p-n junction, I1 and I2 would be one and the same. All the electrons that are injected recombine. In this case, in the BJT, we assume that only a very small proportion recombines. So I2 is a small proportion of I1. And instead, I5 is the majority of I1. So I5 is equal to I1 minus I2. And what is I5? I5 is the collector current. So it is the electrons that manage to be swept into the collector, which is the proportion of I1, the electrons that were injected from the emitter into the base, that does not recombine, because anything that recombines forms a base current. We want I5 to be much larger than I2, which means that collector current is much bigger than base current. Now there are two current components that we haven't looked at yet. Actually just one, which is I6. So what is I6? I6 is actually the emitter current, and it is formed as the summation of I4 and I1. So the emitter current is going to be the summation of holes flowing from the base to the emitter and electrons flowing from the emitter to the base, which should approximately equal I1, because I4 is much smaller than I1. Why are they being added? Because recall that the arrows here represent direction of charge flow, not direction of current, and I1 is an electron flux. And so the emitter current is actually the summation of both I4 and I1. Now, if I6, which is the I emitter, is approximately equals to I1, then that means that the I collector is also approximately equal to the I emitter. So we are seeing, what we want to see here is that the emitter current is mostly formed of electrons. This would happen if I4 is much smaller than I1, and that most of the emitter injected electrons, I1, make it into the collector as I5. So we can basically think of non-idealities of the bipolar junction transistor as I4, which is the opposite kind of charge flowing from the base into the emitter, and also I2 and I3, which form the base current, which is going to eat away from the collector current. So why do we call this a bipolar junction transistor? Again, because it's formed of two junctions, so the junction part is completely justified. Bipolar has to do with the fact that both charge carriers participate in current flow, and that's a little bit misleading because yes, I4 is a whole current, but it should be very small. Again, I3 and I4 are whole fluxes, while everything else in this circuit is an electron flux.